We want our robots to be able to transfer knowledge it has learned from one task to another. For instance, a robot using reinforcement learning may have access to a lot of samples when learning how to assistively feed an able-bodied user. But what happens when the robot needs to now feed a patient with a neck problem, especially when it has access to extremely limited samples? Instead of learning the feeding task from scratch, it should be able to transfer knowledge from the previous task to this one. Our goal is to broaden our understanding of transfer and reinforcement learning by exploring when fine-tuning works, when it doesn't, and how we can overcome its challenges. Many real-life robotics tasks, such as pedestrian navigation, swimming underwater, or simply cleaning your house, involve navigating around obstacles or dangerous states in which the robot would receive a large negative reward if it collided with those obstacles or entered those states. These class of problems can be formalized using the notion of homotopy classes. In this work, we will focus on transfer learning problems where the source and target tasks are in different homotopy classes. So what are homotopy classes? Consider the following running example. A car is trying to navigate to the green dot without colliding with the barrier. Note that this barrier represents any set of undesirable states that give a very large negative reward. So the barrier could be a physical object, like another car, but it could also be a set of unsafe states. And we will show more examples of different types of physical and non-physical barriers later on. Now going back to our example, the car can get to the goal in two ways. It can either swerve right or left. A homotopy class is a set of trajectories that have the same start and end points and can be continuously deformed into one another without hitting any barrier in the middle. So all of these black lines on the right would be in the same homotopy class, and the lines on the left would be in a different homotopy class. In this work, we define a task as a Markov decision process, where the goal is to find a policy parameterized by some parameter theta that maximizes expected discounted return. In this example, the car must find a policy that will take it to the green goal. We have a source and target task where they only differ on the reward function. And we assume that the difference in the reward function represents different preferences or constraints that agents may have that lead to policies that are in different homotopy classes. For instance, the source task can represent the preference of swerving right, and the target captures swerving left. And as you can see, these two trajectories are in different homotopy classes. We assume that the optimal policy parameters for the source task are either known or easily learnable. The goal is then to leverage knowledge from the source policy to learn a good policy in the target task. Concretely, the problem is, after being initialized with the optimal source parameters, can we find parameters that give you near optimal returns in the target task? To gain some intuition on this problem, consider the same fine-tuning problem without the barrier. Let's plot the loss landscape when fine-tuning in the target task. The landscape is relatively smooth. We show a two-dimensional view of this landscape. We are initialized with the optimal source policy parameters on the top left. The optimization is able to find a path towards an optimal set of parameters in the target task. However, when we add a barrier, the loss landscape is no longer smooth and it has a large bump in the middle that stems from the large negative reward given by the barrier. Large negative rewards create gradients that point away from it, making it difficult to fine-tune across the bump. Looking at the 2D view, we see that the source policy is initialized in the same location, but the optimization is stuck in the local optima and is unable to cross the red region. So the problem is that fine-tuning across homotopy classes is hard because of barriers. Our key insight is that we're going to use a curriculum-based approach where we remove and gradually reintroduce the barrier.
Recall that in this example, we want to transfer from the homotopy class MS to the homotopy class MT, but the red barrier makes the fine-tuning difficult. We first remove the barrier from the environment. We emphasize that we only remove the effect of the obstacle in the reward, but do not change the dynamics of the environment. In this case, our dynamics is that the car can go through the obstacle area. We then perform fine-tuning across homotopy classes without the obstacles. Since we use the reward function from the target homotopy class, when fine-tuning, After removing the obstacle, the trajectory of the car will be slightly to the left and move to the desired direction. Then we gradually add back in the obstacle. We start with a part of the obstacle and ensure that the obstacle divides the solid line fine-tuning trajectory and MS into two different homotopy classes. We then perform fine-tuning with the part of the obstacle. Then we inflate the obstacle again. We repeat this process until finally we add back the entire obstacle and achieve the trajectory in the target homotopy class. We have two variants of the ease-in, ease-out algorithm. The first variant is the barrier-sized approach as introduced above. We gradually inflate the barrier size. The reward for each stage can be defined by varying barrier size. Here M is a very large number to punish the agent when colliding with the obstacle. But the variant is suitable only when the barrier is easy to inflate, like when we have a physical obstacle. Also, we show that the method is guaranteed to converge to the target homotopy class using this approach. When the obstacle is difficult to inflate, we employ the reward weight method to achieve our ease-in, ease-out algorithm. In the reward of each stage, we discount the punishment of colliding with the obstacle by a parameter alpha k. This method is suitable for any kinds of reward functions but is not guaranteed to converge. But we demonstrate that the policy becomes closer to the target homotopy class at every stage. We will evaluate our algorithm using a number of simulation environments. First, we study how varying barrier sizes can influence our algorithm and other baselines. Large barrier sizes makes fine-tuning more difficult, and the results suggest that our method is especially useful when barriers are large. When fine-tuning is easy, methods like PN or simpler approaches like starting from a random initialization can be used. We next evaluate how the number of obstacles or homotopy classes affect our algorithm and the other methods. Adding a second barrier creates 4 homotopy classes as shown by the figures where the car can go left twice, left then right, right then left, or right twice. The task is to see how well the car can learn the latter 3 tasks when initialized with going left twice. We experimented with both barrier size and reward weight approaches. Our approaches are able to fine-tune the most efficiently. Compared to the rest of the approaches, as most of them required more than 300k steps, we conclude that while increasing the number of barriers can make fine-tuning more difficult, it does not negatively affect our approach. As our next evaluation, we will study how barriers in the 3D space can affect things. Here, there are 2 tables, orange and blue, with a pillar in front. In the source task, the fetch robot needs to be reach left to the blue table. And in the target, we want to fetch to learn how to reach right without hitting the pillar, which is the barrier. You can imagine that the fetch is sorting items into these 2 tables. We find that our approach was the most efficient compared to the other baselines. One reason why the baseline did not perform well was that the pillar's large size and the proximity to the robot caused it to collide often, making it difficult to fine-tune. We conclude that our approach can generalize to 3D environments. Finally, we will consider settings where homotopy classes are not defined by physical constraints. In Majorco-end environment, we define barrier states as the set of joint angles the enter's upper right leg cannot move to. Note that this is not a physical barrier, but simply a set of unsafe joint angles. These angles are represented by the red lines. The gray dotted lines are the upper right leg joint limits. In the source task, the ant learns to move while keeping the upper right leg to the bottom of the set of the barrier states. In the target task, we want the ant to move while keeping the leg above the set of barrier states. We find that our approach was the most successful in fine-tuning compared to other methods. In the assistive feeding environment, a robot is learning how to feed a patient with a neck problem. The important thing to pay attention to here is the spoon's orientation. When feeding an able body in the source task, the optimal trajectory requires the spoon to orient upwards. When feeding a disabled body, which is the target task, the spoon needs to be oriented downwards. Barrier states are shown by the red line. One represents a horizontal spoon orientation. This is undesirable because the spoon is most likely to collide with the person's chin or nose. Note again that the barrier is not a physical object, but a set of undesirable spoon orientations. We find that our approach learns the target policy faster than training from scratch, while other methods fail to learn the policy efficiently. Finally, ease-in, ease-out fine-tunes across Homotopic class in a sample-efficient manner across several robotic-inspired simulated environments.